Good day, everyone. I am still Henry Unogu, the biochemist that you know. And today we're going to continue with our videos. I appreciate you all that have sent in your likes, your comments, and wow, all the way from the Philippines. Ken K. Kizi, I trust I pronounced that name very well. I appreciate the questions that you asked, and I am glad that you got satisfaction to those questions. Thank you for following us, for subscribing. And for those of you that have not subscribed, remember on our YouTube channel, go just below the video. You will see the click button for the subscribe. Just click it so that you can follow with our different videos on the sciences. Now today we're going to continue with the last aspect of chemical equilibrium. Now remember the last video we had, I mentioned this word, catalyst. And I told you that a catalyst, all it does is to reduce the activation energy. And I said something very funny. I said the activation energy is the enemy of our reaction. Yeah, some students were asking me, what do you mean by the enemy of a reaction? Yeah, just like we all have enemies. Chemical reactions also have enemies. Now, the enemy of the reaction is what we refer to as the activation energy. Now, I'm just going to define these terms briefly. Remember the catalyst, I said it's an organic compound that speeds up the rate of a chemical reaction. And it does this speeding up by reducing the activation energy. So it looks for a way to reduce the activation energy so that the reaction can be faster. Yeah, so if a reaction can, let's say a reaction that normally should take 2 minutes without a catalyst, if you insert a catalyst, that same reaction can take 20 seconds, 30 seconds. That is what a catalyst does. It creates a new path, a new pathway for the product to be formed. That is what a catalyst does. And remember, we have two major kinds of catalysts. We have the positive and we have the negative. Yes, don't get confused there. Some textbooks will tell you homogeneous and heterogeneous. There are several classifications of your catalyst. I hope you got that. So take note. Now, when we say the positive catalyst, what it does is it reduces the time in the forward reaction. It reduces the time in a forward reaction. Now, for a negative reaction, negative catalyst, instead of it to do what? To reduce the time for that reaction, it will act as an inhibitor. Yeah, preventing the reaction from taking place. That's not a normal one. No wonder it has the name negative. Now, but when we talk about homogeneous, now students tell me, when you hear this word, homo, it has to do with what? Same. Right? Yeah, sure, same. So in homogeneous catalysis, what happens here is the reactants and products are in the same physical state as your catalyst. While in heterogeneous catalysis, you have the catalyst with a different physical state with that of the reactant and product. Now, let's not waste our time there. Let's explain this based on activation energy. Yeah, you all got me with the board today, right? Yes. I have some illustrations to make, and that is why I had to bring this board. Look at this. Let me draw an energy profile diagram. Take note. Yeah, I'm a good artist. I have A plus B, referring to our reactants, and I have C plus D as our product. Yeah, up here, this is my activated complex. From this point, the activated complex to where the reactant is, that is my activation energy. You see that, the enemy of our reaction. That is the activation energy. It has no business with our product. Remember, it prevents this product from being formed. And that is why this line drawn, it gets to where your reactant is. This is my activation energy. Now, this reaction is without a catalyst. Now, what do you think will happen if I introduce a catalyst? Here, if I introduce a catalyst, our wonderful positive catalyst will create a new pathway. So instead of the reaction going this way, you will notice that the reaction will take a new path. A shortcut, right? Of course. So instead of the reaction taking, let's say, 20 minutes to travel this long distance, the reaction will prefer to go through a shorter distance. Now that is what a catalyst does in every chemical reaction. It reduces the time for a product to be formed. Now remember, our activation energy is the minimum energy barrier that reactant particles must overcome for a reaction to take place. The minimum energy barrier that reactant particles, I told you it has to do with reactants and not products, that reactant particles must overcome for a reaction to take place. Now when we come to energy changes in a chemical reaction, where we start looking at basic endothermic and exothermic reaction, this will be explained very well. This will be properly explained. You will understand that we have an energy profile diagram for endothermic and we have the energy profile diagram for exothermic. Yes, every chemical reaction in nature is accompanied by different energy changes. Now the energy changes can either be in the form of heat, it can be in the form of light, and of course, it can be in the form of sound. So every chemical reaction is accompanied by one of these energy changes, in form of heat, in the form of light, or even the form of sound. Now, the question is, how do you see all of this? In simple chemical reactions, for example, pardon me, let me take this one off. In a simple chemical reaction, let's say, for example, we have this calcium triazocarbonate 4, a solid. Always remember to put your physical state. This is giving me calcium oxide and carbon dioxide. This is a gas and this is a solid. Now look at this reaction. Take note, my limestone, this can be called limestone. This can also be called marble. This can also be called calcium triazocarbonate 4. You see, as a chemistry student, you must not only know the IUPAC nomenclature of a particular compound. Old names are also important. You must know the old names too. I hope you got that. So this is called either our limestone, and our limestone upon decomposition gives us calcium oxide and carbon dioxide. Now look at this, just a forward reaction. It shows you that this reaction is in an open system, not closed. It's in an open system. So as our gas is giving off, there is no way that carbon dioxide can recombine with calcium oxide to give us calcium triazocarbonate 4. But if the reaction were written in this form, take note of the difference between these two. Here plus carbon dioxide gas. Now take note, the same reaction, but here a forward and a backward reaction. It shows that this system is a closed one. This is an open one. I remember what I explained about open and closed system in our video on chemical equilibrium. I told you that an open system, once the gas is evolved, it will travel out of the environment, the surrounding, and there is no way it can recombine to form reactants. But in a closed system, this is a closed aperture. It prevents the escape of a gas. So as my gas is produced, it's still within that environment. It is not lost, yes. So it can recombine with calcium oxide to give us back our initial reactant. And that is why you have forward and backward. So this can break up to give these two. These two can recombine to form this, only in a closed system. Now look at this reaction. This reaction has an enthalpy change of plus X kilojoules per mole. Pay no mind to the X. Our interest is just in this symbol, the positive. So here, heat is absorbed because this is an endothermic reaction. So what if they ask you to write, what if you were asked to write the equilibrium constant? Since we are talking about equilibrium, if you are asked to write the equilibrium constant for this reaction, how would you do that? Remember, our equilibrium constants can be our KEQ or our KP. The difference between them is here we're talking about partial pressure. That's why you have your P, partial pressure. But for this equilibrium constant, our interest, we are working with molar concentration. We're working with molar concentration. Please take note of the difference between these two equilibrium constants. Here, we're looking at molar concentration, but for your KP, we're working with partial pressure. So our interest is not in any other physical state, but pressure. Remember, we have other physical states. We have solid, we have liquid as physical states. I hope you got that. So we have that. But here, our interest is just on gases. And that is why it is what? Partial pressure. So if you are given this chemical reaction, let's say your exams or whatever, and you are asked to write the equilibrium constant, KEQ, for this reaction, and also to write the KP, the equilibrium constant for the partial pressure for this same reaction, how would you do that? I'll teach you an easy way to do that. Just follow me. I want you to take note that equilibrium constant, remember this is the one that deals with molar concentration. It is the concentration of products divided by the concentration of the reactant. Take note, this bracket, this square bracket, deals with molar concentration. It's different from this. Take note, two different brackets. We're not working with this one. We're working with this, a square bracket. So molar concentration of the product divided by the molar concentration of the reactant. All right. Now, but in this chemical reaction, look at this. This is not dissolved in water. This is in a solid state. This is also in a solid state. So, of course, we cannot get the concentration of that. It has not been dissolved in any liquid whatsoever. So, there is no way we can write this. So, if I'm going to get my KEQ for products, remember, this is my reactant on the left. This is my product on the right. So, the equilibrium constants for the product. Look at this. Which one is the gas? Carbon dioxide is the gas. So what you will do is concentration of CO2. And that is my KEQ for that reaction. Easy, ain't it? Yeah, very easy. Just follow that. Remember, concentration of products, concentration of reactant. We did not include this and this. Why? Because they are in the solid state. This is the only gaseous state. I trust you understand. Now, if I'm going to reverse this reaction, what if we have this? Calcium I have my calcium oxide, a solid, plus carbon dioxide, a gas, giving me calcium tricarbonate 4, a solid. And you're asked to get the KEQ, the equilibrium constant for this reaction. Now, this is my product, and these are my reactants. But look at the product. Did you see any gas? Oh no. No concentration, not dissolved in water. So we cannot get the molar concentration for this one. We cannot write it out in this form. And since there is no gas, the product side is gone. But the reactant side, I have a gas, carbon dioxide. So that's molar concentration of CO2. Are we going to leave it this way? Oh no. You just put a 1 above. And that is my answer. You see the difference between them. Now, but if you're going to get the KP for the reaction, look at the difference between them. We said KP deals with partial pressure. The KP is still the partial pressure of products divided by the partial pressure of the reactant. This funny looking symbol represents the partial pressure. Now, since we're dealing with just gases, if I am going to write the equilibrium constant, the KP, for this reaction, that is product over reactant. Any gas in the products? Oh no, So that gone, you just leave it as 1 over. We have a gas in the reactant, and the reactant is below. So it will be partial pressure of CO2. And that is my answer. So you got that. So this is my KEQ, the equilibrium constant for molar concentration, and look at this for partial pressure. But remember, if they were all gases, for KEQ, it would just be concentration of product divided by concentration of reactant. Let me quickly write this out. What if you had this? Let me just finally put this. I have nitrogen gas plus hydrogen gas to give me ammonia, the production of ammonia. What if I had this? Balance, right? Hydrogen 6, nitrogen 2, yes. They are all gases. So if I'm going to write the equilibrium constant for molar concentrations, what will I do? Product, that is ammonia. You write it. Don't include the coefficient. The coefficient will act as a power. 2, all divided by, they are all gases. So that of this is N2. Coefficient is just 1, neglect, times hydrogen gas and 3. That will be this. Why for the partial pressure, it will be partial pressure of ammonia all raised to power 2 divided by partial pressure of nitrogen times the partial pressure of hydrogen all raised to power 3. I trust you understand this. So this is how you get your partial pressure for both the equilibrium constant KEQ and that of your KB. I trust you understand this. This is the last aspect of equilibrium, where you deal with catalysts, writing out KEQ, the equilibrium constant for molar concentration, and the equilibrium constant when you have a partial pressure. Now remember, in our next video, we'll be looking at chemical changes. I told you chemical changes are everywhere. And I trust some of you, you walk behind, under an electric cable, a high tension cable. I trust you keep hearing that sound. A student once asked me that. What is that sound? When you walk under an electric cable, you hear it, one buzzing sound. What is that? It's a chemical reaction. It's as a result of what? Electric current and air. Ionization. That is why you have that. And do you know what? It is actually called a coronal discharge. Yeah, funnily enough, different from our coronavirus. Take note. Now, remember, coronal discharge. We're going to discuss this when we come to energy changes. This is where I end my video for equilibrium. Watch out for the next video. And remember, don't forget, go to our Facebook channel, go to our Instagram channel, The Simplifier 1. Like it, comment. And don't forget, please don't forget, go to our YouTube channel and click on that subscribe button, The Simplifier 1. Thank you very much. I'll see you in the next video. Bye.